So we can see here that after a lot of hard work, we finally have the del squared operator. And that's beautiful because now we can finally relate back to the Hamiltonian. Because the Hamiltonian itself is minus h bar squared on 2m times the Laplacian operator. And then, of course, we also have the potential pieces that we've been looking at. And so now we can substitute this new hard-won expression in for del squared. So the first piece will give me minus h bar squared on 2m times what must be the radial portion of the kinetic energy, which must go something like then 1 over r d by dr squared of r. So it looks kind of like what we would expect, two derivatives with respect to r, but there's these extra pieces that are coming in because of the complexities of dealing in spherical coordinates. Okay, now we also have to put minus h bar squared on 2m multiplying these pieces. The h bar squares will cancel out nicely. The minus signs cancel out nicely. So I'm left with plus 1 over 2m r squared times then the angular momentum operator squared. And remember, this only acts on thetas and phi. So I could write a little subscript to remind us that this acts on thetas and phi's only. And, of course, let's not forget we need our potential z, Coulomb's constant, e squared times 1 over r. Now, the next step in our analysis, now that we have our Hamiltonian, is to recognize that this Hamiltonian structure comes in pieces, right? There's two pieces here that depend only on radius, and only one piece depends upon angle. So this strongly suggests that we should attempt the standard technique in differential equations, which is known as separation of variables. We're going to see if we can argue that, in fact, any general solution to the time-independent Schrödinger equation can be written, if it's in polar coordinates, in a separated product form as a product of one piece that depends only on the radius and another piece then that depends on just these angles. And I will call that piece, for reasons that will become clear, a y as a function of these two angles. So we're going to seek solutions of this form. Later we will justify the fact that when we limited ourselves to this form, in fact, any solution can actually be expressed precisely in this type of a form. But for now, it's just sort of the standard assumption that people use in their analysis of separation of variables. Now, the way to implement this is that we take Schrödinger's equation, E psi equals this Hamiltonian operator up above, applied to psi. And the trick to isolate the portions that depend upon separately r or the angles is to then divide this equation on both sides through by the wave function. So what we really are looking at is something that equals the energy. But the key is that the energy that we're getting from this, let me write E down here, comes in a sum of independent pieces. So let's see how this works. So I'm going to apply this Hamiltonian, right, to this form of my wave function, and then I'm going to divide by the wave function. Now the Hamiltonian comes as a sum of three parts, so let's focus on the first part first. So when I apply this first part to r times y of theta phi, y of theta phi does not depend on r. That's kind of the point here. And because it doesn't depend on r, when I apply this operator to it, it just can be commuted past everything, right? Because these angles are constants with respect to these derivatives. So when I look at that first term, I'm going to be able to pull out the y of theta phi. Will just come out when this thing applies to my product. I can just pull that out in front, and then I have to, of course, write this operator applied to the remaining pieces, which are h bar squared on twice m 1 over r d by dr squared of the result of r acting on r of r, right? I've got my third parentheses. That's what this operator does to this product, but then the trick is I'm dividing through by psi, and psi itself is just the product of y with r. So I guess I could write it either order, right? I'll write it in my standard order. So psi is just r times y, depends on theta and phi. And the beauty of this is that this y cancels, and the first piece of my equation, notice, now depends only on the radius as a variable. And that's the signature that we are looking for. The next term, we can proceed along, right? So the next term has a 1 over 2mr squared in front of it, fine, plus 1 over 2mr squared. And now I have to apply this with the L squared to this product. Now the same argument works, but in reverse. R, right, of r does not depend at all on the theta or phi variables. It's just a constant with respect to theta and phi. And because L squared only does depend on theta and phi, that r function can just commute immediately past the L squared. So that would give me then on top then my r of r, which commuted through there. The rest of the expression, though, when I am applying this term to my product, the L squared, the r could be pulled out, but the y certainly can't be. So I'm left with then this L hat squared theta, which depends on theta and phi. That was just a reminder to myself. I, formally speaking, don't have to keep writing that, but that acts on y, which depends on thetas and phi's. And this whole term as well has to be divided by psi. That's the beauty of doing this division. And psi is r of r times y, which depends on theta and phi. And in this case, you see how the r's have canceled out very nicely. So I have something now that depends almost entirely just on the angles, right? There's a little bit of r squared piece going on here. We can handle that later, but we can certainly isolate just the angular parts. That's my second term. Finally, I have my third term. But fortunately, the third term is pretty easy to handle. It's minus z Coulomb's constant e squared times 1 over r. Technically speaking, I have to apply that, which is just multiplication, to r of r times y of theta phi. And then, of course, after I've applied h, this piece of h, to my psi, I divide by my psi right back again. So those two terms will very nicely cancel out in both cases. So finally now, the whole idea of the separation of variables is to get all of the r-dependent pieces isolated on one side of the equation and all of the angular pieces on the other side of the equation. And it looks like I should be able to be pretty successful in doing this, right? Here's the angular parts. So let's solve for those angular parts. So I have L hat squared applied to y, which depends on theta and phi. That has to be divided through by y, which depends on theta and phi. Right? Now that's going to equal, I just have to move these two terms onto the same side of the equation with the e, and then multiply by 2mr squared to isolate my remaining piece. So it's 2mr squared. My remaining pieces then are e, right? And then I have to put these guys on the other side of my equation. So he has plus h bar squared on 2m. I'm just copying this term over. When he moved over, he picked up a plus sign. On the numerator, I have two derivatives with respect to r of r times the function r of r, divided by, and in the denominator, I've got little r times big R. So there's little r times big R of r. Good. That's this term moved over. And finally, sorry, the second derivative. Finally, this term is pretty easy. It's just a constant got moved over. Well, it's not a constant, but it doesn't have any functional pieces. It just got added over. So plus z Coulomb's constant e squared times 1 over r. So that now has completely separated my variables. So the final piece of the argument is the standard separation of variables argument. I want you to notice when I think of this function, right? This whole thing could depend upon r, but it's equal to this piece, which doesn't depend on r. So this is independent of r. And because this doesn't depend on r, that tells me that this crazy function, whatever it is, right, has to be a constant with respect to r. Likewise, this term only depends on radius and constants, right? So this is independent of theta and phi. So even though this looks like it might depend upon theta and phi, because it's equal to something that's independent on theta and phi, this implies that this is constant with respect to theta and phi. Now, because this is constant with respect to theta and phi, and it equals something that's constant with respect to r, it's actually constant with respect to everything, r, theta, and phi. So I may as well just give this thing a nice constant name. I'm going to call it a, and a is a constant. And this then gives me two different equations. The angular parts give me equal to a, and the radial parts equal the same a. And I can now deal separately with the two different types of equations. I've reduced my complexity down from a three-dimensional partial differential equation. Now, we should analyze each of these pieces separately. As I've said, we are going to start with the angular momentum piece because we've been thinking a lot about angular momentum lately, and we will move to the radial piece later on in the course. So let's just focus on this equation. Let me rewrite it neatly. So that just says L squared applied to y, which is a function of theta and phi, just actually equals a constant. This is interesting now, isn't it? A constant times my function of theta and phi back again. So this is the equation we're going to be focused on, but this has very important implications. Whenever I have an operator and a function, when I apply the operator, it gives me back the same function with a constant back again. This tells me something very special physically about these y's. These y, theta, phi's are pure states of the angular momentum operator squared. They're pure states of L hat squared. So we're going to be studying now these y's and asking what are the pure states of the square of the angular momentum operator. And those will help us understand the hydrogen atom. And the other interesting thing is we see now how this all comes about naturally by simply thinking about the physics and symmetries of the problem, that this separation of variables should directly lead us to some functions y which actually have a physical meaning in terms of this angular momentum. And we will take up the rest of this discussion in the next lecture.